Sometimes the biggest mysteries in the universe have surprisingly simple solutions. What if I told you there was a single master key that could unlock a whole bunch of cosmic secrets at once? Well, today, that's exactly what we're talking about. We're going to see how just one powerful law of physics solved a puzzle that had scientists scratching their heads for centuries. Let's jump right in. So here's the deal. For the longest time, we knew something weird was going on up in the sky. Astronomers, guys like Johannes Kepler, were watching the planets and they realized, hey, these things aren't moving in perfect circles. Nope. They were zipping around in these kind of squished, oval-shaped paths. And not only that, their speed was all over the place. They'd speed up, then they'd slow way down. I mean, what was going on? What was the secret rule behind all this cosmic craziness? It was a huge, huge mystery. And then along comes Isaac Newton. And let me tell you, he didn't just show up with a hunch. He had the master key, one single brilliant idea that was about to blow the whole thing wide open, unlocking not one, not two, but all three of these puzzles in one fell swoop. Okay, so this was it. This was his key, the law of universal gravitation. And yeah, I know you see that equation and your eyes might start to glaze over, but hang with me. Don't let the math scare you off. The core idea is actually super simple. It just says that everything in the universe that has mass pulls on everything else that has mass. Simple as that. But what does that really mean in practice? Here's the best way to think about it. It's basically the universe's clingy friendship rule. Seriously, if you've got mass, you just can't help but pull other things with mass towards you. It's like an instinct. The sun, the earth, you, me, we're all in on this giant cosmic group hug. So okay, we have this clingy friendship rule. Let's put the key in the lock and see what happens. All right, first up, let's tackle that whole weird, squished circle thing. Why on earth are the planet's orbits so odd? Let's use our new gravity key. So this is what Kepler figured out, his first law. Planets move in ellipses. And an ellipse is, exactly what it sounds like, a squished circle. Imagine a perfect circle that someone kind of sat on. That's our orbit. The big question, though, is why? Why that specific shape and not something else? And this is where Newton's logic is just, well, it's beautiful. Think about it. Step one, the sun is constantly pulling the planet in. That's our clingy friendship rule, right? Gravity at work. Now, this constant tugging keeps the planet from just shooting off into space in a straight line. It forces it into a curve. But, and this is the incredible part, when Newton actually sat down and did the math, after a bit of, let's call it, mathematical wrestling, the curve that popped out of his equations wasn't just any old curve. It was the exact mathematical recipe for an ellipse. No way. I mean, it's like the sun is just telling the Earth what to do. Hey, my gravity is pulling on you just so. And the Earth is like, fine, I guess I'll move in an ellipse then. And just like that, mystery number one, solved. Boom. Okay, one puzzle down, but what about the second one? Why do planets change their speed? I mean, you'd think if gravity is always pulling on them, they just cruise along at a steady pace, right? Well, not so fast. Let's see what our master key has to say about this. This brings us to Kepler's second law, and it's pretty straightforward. When a planet gets close to the sun in its orbit, it really picks up the pace. It just zips right along. But when it swings way out to the far end of that ellipse, it takes its sweet time. It slows right down. So why does this happen? Well, here's the crucial detail from Newton's law. Gravity only pulls straight towards the sun. It's a direct line. There's no sideways nudge, no twisting force, nothing like that. And because of that one fact, a super important property in physics, something called angular momentum, has to be conserved. It has to stay the same. You can think of angular momentum as kind of the amount of oomph a planet has in its orbit. And because gravity doesn't mess with it sideways, that oomph has to stay constant. And this is such a great way to picture it. Imagine the sun is holding the Earth on a leash. When the Earth swings in really close, the leash gets all slack, right? To keep that angular momentum, that oomph, the same, the Earth has to speed up. It's the only way. Then, when it swings way out to the far side, the leash is pulled tight. So what does it do? It has to slow down. It's this perfect cosmic balancing act. Right. It's like the sun is laying down the law. Look, I didn't push you sideways, so you better keep that angular momentum the same, kid. The planet has no choice but to adjust its speed. And with that, puzzle number 2 is officially unlocked. All right, we are 2 for 2. We've got the shape of the orbit, we've got the speed changes, but there's one last piece of the puzzle, The time. Why does a year on Mars take so much longer than a year here on Earth? Let's figure it out. This is Kepler's third law, and it's another one that's simple on the surface. The farther a planet is from the sun, the longer its orbit takes. And I don't mean just a little bit longer. I mean a lot longer. For the planets way out there, we're talking about some seriously long, slow years. So how did Newton's key crack this final code? It's almost magical. He took his law of gravity, he took the standard math for how things move in a circle, and he just smushed them together. He worked through the equations, and then, boom, out pops the exact rule that Kepler had found just by watching the sky. The math just worked perfectly. It showed that the time of the orbit squared is proportional to the distance cubed. It was right there in the numbers. And this little conversation just nails it. The planet asks why its year is taking forever, and the sun's like, because you're far away, my gravity isn't strong enough out there to pull you back very fast. It makes perfect sense, right? The pull is weaker, the planet moves slower, and it has a way bigger track to run. The result? A super long year. And with that, the third and final puzzle is solved. Okay, let's just pause for a second and appreciate what just happened here. We started with 3 completely separate, kind of weird, mysterious rules about how planets fly through space. And we just saw how all of them, every single one, was perfectly explained by Newton's one single law of gravity. This summary just lays it all out. You've got Kepler's law, what he saw. Then you have this simple explanation. And finally, Newton's reason, the why behind it all. The swished circle? That's because gravity gets weaker with distance in a very specific way. The changing speeds? That's all about keeping that angular momentum constant. The long years? That's what happens when you mix gravity with the math of motion. It all just clicks into place. I mean, if there's one thing to take away from all this, it's the incredible power of one single elegant idea. You have 3 totally different cosmic puzzles, and they all get solved by one simple concept, the clingy friendship rule. Honestly, that's the absolute beauty of physics. Think about it. Newton proved that the very same force that makes an apple drop from a tree right here on Earth is the exact same force that keeps the planets locked in their dance around the sun. He literally connected the heavens and the Earth with one equation. And that really makes you wonder, doesn't it? What's the next massive cosmic puzzle out there, just waiting for its master key?